And okay. Good. All right, so we're making a list from this problem. The freezing point constant for water, it gives you, and I've listed it here. The freezing point, so that's the temperature of freezing, okay? That's how we put that in there. Is equal to 0.00 degrees C. And it asks what is the freezing temperature of a 2.50 molar solution. Actually, that's temperature initial. Temperature initial, that's the initial temperature. So that's T, and you can make a little I, capital I don't care, okay? And then the final temperature is going to be that freezing temperature if I have a 2.50 molar solution of NaCl. So the solution's concentration in molality is 2.50 mole concentration. Okay? And let's see, there are two equations we need to use for this. One of these for the change in the freezing temperature, that's change in temperature of freezing, is equal to I, which is the Van Hoff factor, times K sub F, so that's that value right there, times M, which is that value right there. Okay? Now once we've got the change in temperature, then we need this equation, the change in temperature, the final change, I'm sorry, not the change in temperature, the temperature, yeah, that's right, I'm sorry, change in temperature for freezing is equal to the final temperature, so this is temperature final, minus temperature initial. Okay?
Wait, so the triangle.
This is the change in freezing temperature. This is the temperature final, that's temperature initial.
So what the triangle mean?
Change. Delta, this is the Greek letter delta, and it usually means change. Okay? Yes?
I did it this is all without all the hieroglyphics.
Okay, well that's okay. I want you to get to the point you can use the hieroglyphics, okay? Alright, so finding this is a matter of plugging things in. I've already got this one. I need to find I. Since our solute is NaCl, if I take NaCl, that's just table salt, and it's crystalline on your table, okay? When you shake it into water or something and stir it up, you're dissolving it in water, you get sodium ions, and you get chloride ions, and for that, I equals 1, 2. 2 ions, 2 particles it breaks up into. Okay, I is 2. Alright, so now we've got this and this. Oh, hey, I've got that. There it is. Okay, all I need to do is plug it in now. Plug it in, plug it in. That's that what, Glade commercial? Yeah, Glade commercial, right? Alright, so delta T for freezing, is going to be equal to I, which we said is going to be the number 2. That's a counting number now, okay? We're not going to use that for our significant digits. Times K sub F. And K sub F we said is, it's given to you in the problem, is negative 1.86 degrees C over molal. And then times M, which is the molar concentration, 2.50 M. So let's see, we can get rid of the M if we just arrange our fractions so that now molal, the concentration unit, cancels out. And we can find the change in temperature. So we get out our trusty calculator and do some math here. So 2 times a negative 1.86. Now, I hope all of you know you have 2 kinds of buttons that have negatives on your calculator. Okay? On my calculator, this button right here means I'm subtracting. This button right here is what's called the change of sign button. Now, some calculators have a plus and a slash and a negative underneath. Those are both change of sign buttons. Okay? When you want a negative number like this, you need to hit your change of sign button, not your subtraction button. Okay? All right, so we're going to do those two numbers there, and then also times 2.50, and hit enter, and I get a negative 9.3. Negative 9.3. Okay? And let's see, what I have left is degrees C, and this number has 3 digits. This number has 3 digits, 3 significant digits, and this is a counting number. We ignore that one, and we're only going to look at these two numbers. This is a calculated number. This is a measured number. Well, actually, this is calculated. We get right down to it. In either case, those are the only two numbers that matter for figuring out significant digits. So how many digits do I need in my final answer? 3. Okay, now that's the change in temperature. So now that we found the change in temperature from this equation, now we're going to find the final temperature right here from this equation. Oh, sorry. Change in temperature. This is the other equation we'll plug these into. So we have temperature initial from the problem. The problem says that the temperature of the freezing point of water is 0 degrees C. That's always going to be your initial temperature. The freezing temperature of the pure solvent is always the initial temperature. If you haven't written that down somewhere, now would be a really good time. The initial temperature is always the freezing temperature of the pure solvent. Okay? The initial temperature is always the freezing temperature of the pure solvent. Or, if we were doing boiling point, it'd be the boiling point of the pure solvent. Okay? The initial temperature always refers to the freezing or boiling point of the pure solvent. Okay? Pure solvent. In this case, water is the solvent, so it'd be pure water before you put any salt in it. Okay? All right. So now we need this second equation. We just plug things in there. We got delta T of freezing. That's the change in the temperature of freezing. What this means is that's the change from going from the pure solvent to the freezing point of the solution. The temperature, the freezing temperature of the pure solvent to the freezing temperature of the solution. Okay? And then the final temperature is what we got to figure out. That's the final temperature minus the initial temperature. Okay. So we know our delta T is negative 9.30 degrees C. I've calculated it here. Negative 9.30 degrees C, okay, is equal to temperature final, that's what we want to find, minus, okay, temperature initial is the freezing temperature of the pure solvent, and the problem says that's 0. And you really should know that the freezing temperature of water is 0 degrees, right? You don't know that? You didn't know that before? Well, we talked about it a lot. You need to know that. Pure water. And really, it has to be pure water at 1 atmosphere. Okay? But there's not a lot of deviation, even when you go up and down the mountains or something, not a lot. Okay? All right. So let's see. I need to rearrange the equation so I get this by itself. So what I'm going to do is I'm going to add let's see, 0 to both sides, right? So I'm going to add 0.00 to this side and add 0.00 degrees C to this side, okay? And when I add it to this side, I just get TF by itself. That's the final temperature. That's what we're looking for initially. Well, negative 9.30 plus 0 is just, there you go, negative 9. Really? Okay, I'll probably notice that.
Yeah, because it's like 4 point something without the
Yep. So there's your final temperature right there. Yep. Say what now?
Like if you just skip that little process right there after you get your first answer, but you put that as T final, but you went to the last one.
It's not always going to be the same problem, though, really.
I know, I'm talking about that for 0.3.
All right. Are you saying you don't show your work?
Yeah, like.
Okay, you have to show your work. Now, let's say this. Let's just say that you know that the freezing temperature of pure water is 0. And so any depression in temperature we get from this equation is going to be what the final temperature is. That's okay as long as you state that in some kind of sentence or something so that I know that you understand what the math is supposed to be. Okay? For freezing temperature or boiling temperature for just water, nothing else, I would accept that because it is pretty simple when you're adding to 100 or subtracting from 0. Okay? That makes sense? All right, so calculating the change in freezing temperature is plug and chug. The only thing you have to really calculate, if I don't give it to you in the beginning, is the molality. And that's what we've been doing. That's what we did yesterday and the day before, calculating molality. Okay? So, thus far, for the problem yesterday, I went ahead and gave you that. Sorry. So let's give you a problem now where you have to actually figure out the molality for yourself. Okay?